Welcome and thank you for watching this video. My name is Roberto and I'm a principal engineer at ARM, tech leading the developer advocacy team. This video is a short version of the talk I delivered at GDC 2022 on mobile post-processing effects using machine learning style transfer. The topic of this talk is a subject that I find very interesting and promising. I think that style transfer has the potential of becoming a great customization tool in gaming. I hope after the talk you will have an idea of how to use this technique in gaming. The plan is to go first very quick through the concept of style transfer. I will also mention some application of style transfer, especially as a rendering post-processing tool in desktops. Then I will explain in more detail our work to get style transfer working on mobile, the model, the training, and the extension used to optimally share data between Vulkan and machine learning processing space without any copy. Next, I will perform a live demo of our app, and finally, some conclusions. I will also share the step-by-step guide our colleague Pavel Rutku prepared and the link to the GitHub repo so you could reproduce the demo yourself and play with it. Before starting, I would like to say that we are not providing here a solution. We wanted to share some experimental work and inspire developers by showcasing that it's possible to achieve near real-time machine learning post-processing on mobile. Style transfer is a technique in which a neural network takes two images, a content image and a style reference image. Then it copies the texture, colors, and other features of the style image and applies them to the content image. The output image looks like the content image but painted in a certain style. When we started looking at style transfer, we wanted to explore another potential use case, the use of style transfer as a post-processing stage in graphics rendering, as it will allow achieving effects that are not possible to achieve using classical post-processing algorithms. I mean, using machine learning to modify the content of rendered frames. There is an excellent blog from Unity that describes how they achieved real-time style transfer post-processing with their Barracuda inference engine. I guess you are familiar with the NVIDIA deep learning supersampling technology, used today in many games. DLSS allows to render frames in lower resolution and upscale them using a neural network. This improves frame rate significantly, achieving great quality as well. It's also worth mentioning an interesting experiment from Intel Research and collaborators from Apple and Berkeley. They used machine learning to make GTA 5 look incredibly realistic by combining rendering images from the game with the real images from Cityscape datasets of real streets and cars. All these examples run on desktop computers using powerful GPUs. So we wondered whether we could achieve style transfer post-processing with real-time or near real-time performance on mobile. Style transfer is also used in popular mobile applications. It can be applied to photos or videos from phone memory. For example, the Prisma photo editing mobile app allows applying a style transfer to pictures as shown in the left picture on the screen. Some apps, like Snapchat, allow to apply style transfer to pictures and real-time video coming from the camera stream. You can see a video on the right side from Snapchat app that applies style transfer to the camera feed and makes a person look like a character from Simpsons. So we decided to try to implement style transfer as a post-processing effect after rendering a scene with Vulkan. For this, we implemented our own style transfer model, highly optimized for mobile. For the inference, we used the ARM Compute Library, ACL. It is an open source collection of highly optimized functions for Cortex-M CPUs and Mali GPUs. ACL uses an OpenCL compute backend, and it allows you to access some pretty useful low-level functionalities. For rendering, we use a Vulkan sample framework, which is also open source. We use at ARM this framework to share a collection of Vulkan samples in Khronos to showcase Vulkan best practice. An important point was to achieve zero copy when sharing data between Vulkan and OpenCL space for ML post-processing. We will comment in a few minutes about how we achieved this. A few words on neural network model we've used. The model was built from scratch as we wanted it to be as simple as possible to achieve real-time or near real-time performance when running on mobile. The architecture is very small and comprises separable convolutions. They provide better performance than normal convolutions, which is the same solution using MobileNet. First, we do depth-wide convolutions with a 3x3 kernel to gather spatial information. Then we use 1x1 convolutions to gather the info from the channels. Performing these two operations separately reduces the number of computations. These separable convolutions are then combined into larger residual blocks. The entire model has two such residual blocks and an additional separable convolution in the end. To train the model, we sampled a small data set of rendered frames, around 100 frames. This data set demonstrated to be enough for our purpose of applying style transfer to this particular scene. So style transfer will work fine with this scene and probably not as good with others. In general, training for style transfer networks is quite complicated and involves using other neural networks to calculate perceptual loss as the difference between image features. The network must produce pictures that look like the content and reference image at the same time. So this approach allows you to use any style transfer image. So this is a flexible solution. But in our case, we were not looking for flexibility, but compactness. So we decided to implement a less flexible, but more robust option, which takes only the content image as an input. In this case, the style information is embedded into the model. So for training, we wanted just to get things working with our lightweight model, so we use a particular approach. Remember, we dumped 100 images for our data set. So we processed this entire data set using an already pre-trained style transfer network from an article by TensorFlow. So this network provides style output image for each input content image. We signal this more rigorous network as the big one. We have now 100 pairs of images, content and stylized image, and we use them to train our model. This time, we were able to use a simple mean square error function to train our smaller model. But the main point was to embed this model into a graphics application. After rendering the scene to an off-screen image in Vulkan, we import the image to a native Android hardware buffer. The Android hardware buffer represents chunks of memory that can be accessed by several hardware components in the system. The Android hardware buffer is imported directly into OpenCL using CLARM import memory extension as a CLMem handle. Moreover, the data is directly imported as a CL tensor that is passed to the ARM compute library to apply the style transfer. All this happens with zero copy, thanks to the Android hardware buffer and the OpenCL extension. And now let me show you the style transfer post-processing app running on a Samsung Galaxy S21 equipped with an ARM Mali GPU G78 with 14 cores. As you can see, When the style transfer post-processing is not enabled, the Vulkan app runs at 60 FPS or more. So let's enable the style transfer post-processing. We can see that the FPS now is around 30 frames per second, and I can move the camera around smoothly. Definitely, the style transfer post-processing adds a significant workload to the GPU, but it still can respond smoothly to the camera movements. Finally, some quick conclusions. First, ML is opening new possibilities in mobile graphics, especially on rendering, where we haven't seen really many improvements lately. In this regard, ML is bringing fresh air to mobile graphics and gaming. Looking at a style transfer, I can see it as a great optimization tool, and I can imagine games with different rendering styles in different levels. Ultimately, the user will be able to apply his own style. There will be needed, of course, some work by artists and developers to create the tools to define the right style image to achieve a given visual effect. Regarding the extensions needed to share data between Vulkan and the machine learning processing space, Khronos is working on a new extension to enable Vulkan ML interop, and they should become available to developers next year. As you can see, now mobile ML post-processing is challenging, but we can expect to be easier in the future and definitely very rewarding. We will be able to achieve visual effects we can't achieve now with the standard post-processing techniques. Hope you have found this talk interesting. Thank you very much for watching this video. But before finishing, I will share a couple of links where you could have more detailed info of this work and the demo itself. So you can find a detailed step-by-step guide written by my colleague Pavel Rudko in the ARM Compute blog, Style Transfer for Graphics Post-Processing on Mobile. Also, in the GitHub repo, you can download the source code of the app, the model, and the dataset to reproduce this demo. With this slide, I finish the video. Thank you very much for watching.